Hello there, welcome to Ethio-Hahu tutorial. I'm Ethio and today I'm going to discuss about quantity of heat and calorimetry. In the previous videos, I've discussed about heat and temperature. It's a form of energy that is transferred from one point in space to the other point in space as a result of difference in temperatures by different mechanisms. Such mechanisms are conduction, convection, and radiation. And temperature is a measure of average molecular kinetic energy of a system. Also, temperature determines the direction of heat flows. We have seen these two concepts in the previous videos. Today, we are going to see about the quantity of heat added to the system, the quantity of heat extracted from the system, specific capacities, heat capacities, latent heat of fusion, latent heat of vaporization, and phase change. It's a form of energy with SI unit joule. But there are other units called calories and British thermal unit. 1 calorie is 4.184 joule and 1 British thermal unit is 1054 joule. Having seen this, how can heat be added or extracted from a system? As we have said, when two systems are maintained at different temperatures, the system with higher temperature loses thermal energy, whereas the system with lower temperature gains thermal energy. To add heat to a system, we need to bring that system in contact with a hot reservoir with a system of higher temperature, so that the system with a higher temperature loses energy and the system that we are interested in gains energy. And in this way, we add heat to the system. Let's consider system A. In order to add heat to the system has to be in contact with another system of higher temperature. This is hot reservoir. And from this hot reservoir, thermal energy will be added to the system. Therefore, heat is added to system A in this case. If we want to extract heat from a system, the system should be in contact with another system of lower temperature. Therefore, bring the system in contact with a cold reservoir so that the system of interest loses thermal energy. Here we have system B with temperature TH, higher temperature, and here we have cold reservoir. If we bring this hot system in contact with a cold reservoir, the system loses thermal energy to the cold reservoir. Therefore, the direction of heat flow is from the system to the cold reservoir. This is heat lost or extracted from the system. By this, we can extract heat from the system. Having seen this, let's see specific capacity and heat capacity. The specific heat capacity of a substance is the quantity of heat required to change the temperature of unit mass of substance by 1 degree Celsius. The SI unit of a specific heat capacity is joule per kilogram per Kelvin, but non-SI unit of a specific heat capacity is calorie per gram per degree Celsius. The heat capacity of a body is the quantity of heat required to raise the temperature of the whole system or body by 1 degree Celsius. The difference between specific capacity and heat capacity is, in a specific capacity, the quantity of heat is required to raise the temperature of a unit mass of a substance, 1 gram or 1 kilogram of a substance, by 1 degree centigrade, whereas heat capacity is the quantity of heat required to raise the temperature of the whole system by 1 degree Celsius. Heat capacity is simply mass times a specific heat capacity. C is equal to the quantity of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius. Multiplying both sides by M, simply M times C is equal to delta Q divided by delta T. But delta Q by delta T is heat capacity, capital C. This heat capacity is simply mass times a specific heat capacity. What is latent heat of fusion or heat of fusion? Heat of fusion of a crystalline solid is the quantity of heat required to melt a unit mass of the solid at constant temperature. This is also equal to the quantity of heat given off by a unit mass of a molten solid as it crystallizes at this same temperature. If we take water as an example, heat of fusion of water at 0 degrees Celsius is about 335 kilojoule per kilogram or 80 calorie per gram. Whereas heat of vaporization or latent heat of vaporization of a liquid is the quantity of heat required to convert a unit mass of a liquid to steam at constant temperature. Again, if we take water as an example, latent heat of vaporization of water at 100 degrees Celsius is about 2.26 megajoule per kilogram or 540 calorie per gram. To see this, let's consider water. As we know, most substances exist in solid state, liquid state, and gaseous state. Water can exist in the form of solid state, in the form of liquid state, and in the form of gaseous state. To see this, let's consider this axis. This axis is heat added to the system, and this axis is temperature in degrees Celsius. This one is 0 degrees Celsius. This one is 100 degrees Celsius. This is solid state. Water exists in the form of ice at 0 degrees Celsius and below 0 degrees Celsius. Therefore, assume that this temperature is, say, minus 10 degrees Celsius. If we want to increase the temperature of ice from negative 10 degrees Celsius to 0 degrees Celsius, we need to add heat to the system. Once this ice reaches 0 degrees Celsius, even though we add heat to the system, the temperature remains constant, and this state is known as phase change from solid state to liquid state. At 0 degrees Celsius, totally the solid state is converted to that of liquid state, but still the temperature is 0 degrees Celsius, and this point is the point where solid state and liquid state coexist. Once the solid state is totally converted to liquid state, by adding heat to the system's temperature increases from 0 degrees Celsius to 100 degrees Celsius. Once the liquid reaches 100 degrees Celsius, even though we add heat to this liquid, the temperature remains the same. Where does this added thermal energy go? This thermal energy brings phase change from liquid state to gaseous state. And at this 100 degrees Celsius, water and steam or vapor coexist. Then, totally, if the liquid is converted to that of vapor state or steam, upon adding heat to the system's temperature will rise from 100 degrees Celsius to a temperature above 100 degrees Celsius. Therefore, at this point we have liquid, at this point we have steam. But at this point, liquid, steam coexist. At this point, solid, liquid coexist. In order to increase the temperature of ice from negative 10 degrees Celsius to that of T, we need to add this amount of thermal energy, that is Q1, the first energy, so as to change the temperature from negative 10 degrees Celsius to 0 degrees Celsius. Heat of fusion, the amount of heat needed to melt totally the solid into liquid state. Once we have liquid state, upon adding heat to the system's temperature will rise to 100 degrees Celsius. And when it reaches 100 degrees Celsius, even though we add heat to the system's temperature remains the same, but there is phase change from liquid state to that of gaseous state. And upon adding heat further to this system, the system's temperature rise above 100 degrees Celsius. Therefore, in general, the amount of heat that we add to a system can partly increase the temperature of the system and partly does work on the system. When we say that the amount of heat added to the system partly does work on the system, it brings phase change from, say, solid state to that of liquid state, and from liquid state to that of vapor state or steam. Having seen this, let's see the concept of calorimetry. The quantity of heat gained or lost by a body of mass m and a specific heat capacity c whose phase does not change is, for temperature delta T, is given by this: delta Q is equal to m times c times delta T. Since we have seen a specific capacity of a substance is the quantity of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius. Therefore, from this, delta Q is equal to m times c times delta T. This is the quantity of heat added to the system or extracted from the system. Calorimetry helps determine the amount of heat exchanged between a system and its surrounding. When two systems at different temperatures are brought in contact, say system A and system B, A at temperature T1 and B at temperature T2. If T1 is greater than T2, system A loses thermal energy and system B gains thermal energy. Assuming that there is no loss of thermal energy to the surrounding, the amount of heat lost by system A is the same as the amount of heat gained by system B. Therefore, heat lost by A is the same as heat gained by B. This is from conservation of energy. Therefore, when two substances at different temperatures are brought in contact, they exchange heat energy, and the quantity of heat lost by the hot substance is the same as the quantity of heat gained by the cold substance. And this concept, the exchange of thermal energy between two systems at different temperatures, is known as calorimetry. Therefore, calorimetry helps to determine the amount of heat exchanged between two systems. Having seen this, let's see examples. The first example says that how much heat is required to heat 250 grams of water from 20 degrees Celsius to 50 degrees Celsius. The specific capacity of water is 4.2 kilojoule per kilogram per degree Celsius or Kelvin. To do this, mass is given 250 grams. The initial temperature is 20 degrees Celsius and the final temperature is T2 is equal to 50 degrees Celsius, and the specific capacity of water is equal to 4.2 kilojoule per kilogram per degree Celsius or Kelvin. Therefore, the quantity of heat required to raise the temperature of 250 grams of water from 20 degrees Celsius to that of 50 degrees Celsius is obtained by this: delta Q is equal to m times c times C of water times delta T, and this implies m times C of water times delta T is T2 final temperature minus T1 initial temperature. This implies delta Q is equal to m is in SI unit is equal to 250 times 10 to the power of minus 3 kilogram, because gram is 10 to the power of negative 3. 250 times 10 to the power of minus 3 kilogram. The specific capacity of water is 4.2. 4.2 times 10 to the power of 3 kilojoule means 10 to the power of 3 joule per kilogram per degree Celsius times T2 minus T1. T2 is 50 degrees Celsius minus T1 is 20 degree Celsius. This is equal to 250 times 4.2 times 10 to the power of minus 3 times 10 to the power of 3 kilogram goes with kilogram, degree Celsius goes with degree Celsius, times 50 degrees Celsius minus 20 degrees Celsius is 30 degrees Celsius, and but degree Celsius goes with degree Celsius, and we are left with joule. This 10 to the power of negative 3 by 10 to the power of 3 goes, and this is equal to 250 times 4.2 times 30 joule, and this is equal to 31.5 kilojoule. This is the quantity of heat required to raise the temperature of 250 grams of water from 20 degrees Celsius to 50 degrees Celsius. When we come to the second example, what will be the final temperature of 50 grams of water at 0 degrees Celsius is added to 250 grams of water at 90 degrees Celsius. Again, given there are two systems. One is at temperature 0 degrees Celsius and the other is at 90 degrees Celsius. And if we bring these systems together, they exchange energy. The system with higher temperature loses energy, whereas the system with lower temperature gains energy. Therefore, here we have M1. M1 is 50 grams. T1 naught. Initial temperature of the first system is 0 degrees Celsius. M2 is 250 grams and T2 naught. The initial temperature of M2 is 90 degrees Celsius. This is cold and this is hot. If we bring these two systems together, here we have final temperature. This is T01 and T02. T01 is the initial temperature of system 1 and T02 is the initial temperature of system 2 with mass 250 grams, and T is the final temperature of the system. Therefore, when we add these two systems, one at 90 degrees Celsius and the other at 0 degrees Celsius, then the water with 90 degrees Celsius loses thermal energy, whereas the water with 0 degrees Celsius gains thermal energy. Therefore, the equilibrium temperature T is greater than 0 degrees Celsius and less than 90 degrees Celsius. This T is unknown, but less than 90 degrees Celsius and greater than 0 degrees Celsius that we are going to find. Therefore, from heat exchange, heat lost by the hot system is equal to heat gained by the cold system. Heat lost by the hot system is this one, M2 C times delta T2 is equal to M1 times C delta T1. Here delta T1 is equal to T minus T1 naught, and delta T2 is simply 90 minus T, because the final temperature of the two systems is T. This implies M2 is 250 grams times they have the same specific heat capacity, C, 1 calorie per gram per degree Celsius times delta T2. Delta T2 is 90 minus T. This is equal to M1 is 50 grams times C is 1 calorie per gram per degree Celsius times delta T is T minus 0. Here 1 calorie per gram per degree Celsius with 1 calorie per gram per degree Celsius. Gram goes with gram. Here 1 0 goes with 1 0. By 5 1, by 5 5. 5 into 90 minus T. That's equal to simply T. 5 times 90, 450, minus 5 times T, 5T. That's equal to T. If we bring this minus 5T to the right, 450 degrees Celsius is equal to 5T plus T. 450 degrees Celsius is equal to 60, and dividing both sides by 6, T is equal to 75 degrees Celsius. The third example, how much heat is required by 10 grams of ice at negative 10 degrees Celsius to change to steam at 100 degrees Celsius. Use a specific capacity of ice 0.5 calorie per gram per degree Celsius, a specific capacity of water 1 calorie per gram per degree Celsius, heat of fusion of water 80 calorie per gram and heat of vaporization 540 calorie per gram. To do this, M is 10 gram. First, let's draw the free body diagram. This is heat, delta Q, and this one is temperature. This is 0 degrees Celsius. This is 100 degrees Celsius. And the ice is at minus 20 degrees Celsius. This is minus 20 degrees Celsius. To increase the temperature of ice from negative 20 degrees Celsius to 0 degrees Celsius, we need to add heat delta Q1. Once 0 degrees Celsius is reached, upon adding delta QF, heat of fusion, the temperature of the ice remains the same, but there is a phase change from solid state to liquid state. Once we have liquid state, upon adding to the liquid, the temperature will increase up to 100 degrees Celsius. This is delta Q2. Once the temperature reaches 100 degrees Celsius, upon adding heat to the system, delta QV, there is phase change at same temperature 100 degrees Celsius. And if we add further heat to the system, there is temperature rise from 100 degrees Celsius to a temperature which is above 100 degrees Celsius. We have phase change at 0 degrees Celsius and only at 100 degrees Celsius. Therefore, we want to find the amount of heat required to change 10 grams of ice from negative 20 degrees Celsius to a steam at 100 degrees Celsius up to this point. Therefore, total energy Q is equal to delta Q1 plus heat of fusion plus delta Q2 plus heat of vaporization. This is the total amount of heat needed to change ice, 10 grams of ice at negative 20 degrees Celsius to a steam at 100 degrees Celsius. Delta Q1 is simply mass of ice times C of ice times delta T of ice plus delta QF is mass of ice times heat of fusion plus delta Q2 is mass of water times C of water times delta T plus heat of vaporization is mass of water times latent heat of vaporization. Mass is 10 gram. 10 gram times the specific capacity of ice is 0.5 calorie per gram per degree Celsius times delta T, change in temperature from negative 20 degrees Celsius to 0 degrees Celsius is simply 0 minus 20 is plus 20 degrees Celsius plus mass is 10 gram times heat of fusion is 80 calorie per gram plus mass of water 10 gram times a specific capacity of water 1 calorie per gram per degree Celsius times delta T is from 0 to 100 minus 0 plus mass 10 gram times heat of vaporization 540 calorie per gram. Here gram goes with gram, degree Celsius goes with degree Celsius. 10 times 0.5 is 5, 5 times 20 is 100 calorie plus gram goes with gram, 10 times 80, 800 calorie plus 10 gram, gram goes with gram, degree Celsius goes with degree Celsius, 100 times 10, 1000 calorie plus gram goes with gram, 10 times 540 calorie, 5400 calories, and this is equal to 7.3 kilocalorie. This is the total amount of heat needed to raise the temperature of 10 grams of ice at negative 20 degrees Celsius to steam at 100 degrees Celsius. This is all about today. Next, we'll see another topic. Until then, have a nice time.